Today, we want to talk about why conditional convergence is a weaker condition than absolute convergence and why we have these two different types of convergence. We're going to do this using our favorite conditionally convergent series, the alternating harmonic series. The alternating harmonic series is in fact alternating, and the terms decrease to zero, which gives us convergence by the alternating series test. But in absolute value, the harmonic series, if we remove the alternating, the harmonic series, we know diverges based on the integral test or because of the P series, which is actually because of the integral test. So because of the integral test. Since the alternating harmonic series converges, it must have a finite sum. Since the alternating harmonic series converges, the sum must be finite. So let's let S be the sum of the alternating harmonic series. Let S be the sum of the alternating harmonic series. Now we're going to do some algebraic manipulation. I want to take this sum, this alternating harmonic series, and I'm going to multiply everything by 1/2. Since the alternating harmonic series is convergent, I can multiply every term by a constant, still get convergence, and the sum will just be that multiple of the original sum of the series. We can factor stuff out, and that is okay. So we're going to multiply everything by 1/2. So I'm going to rewrite this series with where everything is multiplied by 1/2. It's going to be a 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 and so on, minus 1/12 and so on. Moreover, the sum, when I multiply all the terms by 1/2, will just also be multiplied by 1/2. In a convergent series, we can factor out constants. The distributive property holds in a convergent series. As long as we multiply it by not just 0. So if we have a divergent series, we can't just multiply by 0 and say, oh, now it converges. That doesn't make any sense. That just zeroes out all the terms. But when we have a convergent series, we can distribute. The distribution that I'm talking about clearly is multiplication over addition because a series represents a sum. Now what we're going to do is I'm going to add spacers. I'm going to shim my 1/2 alternating harmonic series. I'm going to take my half series and we're going to add zeros as spacers. So in front of the 1/2, I'm going to put a 0. And then we'll have a plus 1/2. And then we'll have a 0. And then we'll have our minus 1/4. And then we'll add 0. And then we'll have our plus 1/6, and so on. All we've done here is added 0. We have literally added nothing. The series, they're all just 0. Now this series, this half alternating harmonic series converges, and our original alternating harmonic series converges. So we know that we have the sum of convergent series is convergent. So I'm going to add my spaced out half alternating harmonic series with my original alternating harmonic series. I'm going to take my half alternating harmonic series, my spaced out half alternating harmonic series, and add my original alternating harmonic series. Both of these series are convergent, so their sum will be a convergent series. We're just using the fact that the sum of two convergent series is also convergent. So I get 1 minus a half, plus a half minus a half is 0. 0 plus 1/3 is plus 1/3. Minus a fourth is minus 2/4, or minus 1/2. 0 and a fifth is a fifth. The plus 1/6 minus a 6 cancels out. 0 and 1/7 is 1/7. Negative 1/8 minus another 1/8 is negative 2/8, otherwise known as negative 1/4. And we can see what the pattern is going to be. And instead of going denominators odd, even, odd, even, odd, even, my denominators is just going odd, odd, even, odd, odd, even, odd, odd, even. So we can see what the rest of this series is going to look like. We can see that after this, we'll have a plus 1/7 minus a fourth, plus 1/9. Then some terms will cancel out, and the next three will be the 11th, 1/11, minus a 6th, plus a 13th. So we have just the sum of two convergent series is also convergent. Moreover, the sum of those series, the sum of our sum of series will be the sums of the two series. So we can get the sum of our new series by just adding the sums of our half, our spaced out half alternating harmonic series and add that to the sum of our regular alternating harmonic series. The sum of convergent series is convergent, and the sum of the total series is the sum of the individual fact terms. Sum of the two convergent series is convergent, and the sum is the sum. Any questions? Nothing on my screen. Now look at our series, where which is the sum of the alternating harmonic series and our spaced out half alternating harmonic series. Look at this series right here. It's not alternating, it's not harmonic, but it has all the same terms as the harmonic series. This is just a rearrangement of the terms in the harmonic series. This sum that we created is just a rearrangement of the terms of the alternating harmonic series. By this process, all we have done is rearranged the alternating harmonic series. And when we rearranged the alternating harmonic series, we ended up with a different sum. We have rearranged the terms and got a different sum. The order that we added the terms changed the sum of the series. This is not normal behavior for addition. Addition is normally commutative. A plus B is equal to B plus A. But when there's an infinite number of terms and your series is conditionally convergent, the order that you add the terms changes the sum. Addition is not commutative in a conditionally convergent series because infinity is really weird. Normally, addition is commutative. We do A plus B is the same as B plus A. But here in this conditionally convergent series, yeah, we're getting a sum, but changing the order that we add stuff will change the sum of the series. So when you ask the question, that's why you asked for this, by the way. When you ask the question, what is the sum of this series? My response, since it's conditionally convergent, is what do you want the sum to be? And then we'll rearrange the terms to make that happen. This kind of funky behavior does not happen in an absolutely convergent series. Absolutely convergent series is always the same sum. This is the difference between conditional convergence and absolute convergence. Absolute convergence is more reliable. It doesn't matter what order we write the terms, we always get the same sum. In a conditionally convergent series, if we start rearranging the terms, we can rearrange the terms into a different sum. So if someone says, what is the sum of this conditionally convergent series? Just say, yes. But when someone says, what is the sum of this absolutely convergent series? You need to say, well, how much computing power do you have? And how many decimal places do you want? For the most part, this is not that big of a deal, because when I write the sum as n goes from 1 to infinity of the minus 1 to the n plus 1 over n, I have determined what order the terms are going to be written. They're going to be written in this term, in this order. The important thing is to recognize that there is a difference between conditional and absolute convergence, and this is it. You can rearrange the terms into a different sum. And that's weird. If you don't think that that's weird, then I just don't even know. I don't even know how to respond if you don't think that's weird. Maybe you don't think that's weird because like, oh, I knew that math was going to do some weird shit. As soon as you said that we get that, once I understood what a convergent series is, and you said there are two kinds, that I knew math was doing some weird shit, and so maybe you're not surprised by that. It might be that like when there's a bunch of foreshadowing, and then there's the big reveal, and the audience is like, "Oh, well, that wasn't surprising." That's why the foreshadowing was there. The author was telling you what was going to happen. That's what foreshadowing is. The tension comes from the fact that we know what's going to happen, but the characters don't know what's going to happen. That's the tension. Not that the audience doesn't know what's going to happen. You know what I mean? That's why I thought it would have been dope if the MCU ended whatever phase it was, phase 3. Just at the snap, just like this is the new reality. So, well, what happened to those characters? They got snapped out of existence, and then just started making other movies. So, is there going to be another Spider-Man movie? Well, yeah. Oh, good. So he's coming back. Nah, there's going to be a prequel. We're going to have. Oh, shit. What about those characters? Oh, they snapped out of existence. No, you have to fix it. That'd be a great rug, one of the great rug pulls in cinematic history. If Disney was like, oh, no, that's the last Marvel movie that we're making. All right. Thing you got to watch out for as far as Marvel commentary goes. If anybody who's like, oh, Thanos was right, watch out for that fucker. Make sure that that fucker is never in charge of anything. Anybody that agrees that Thanos is right, you are wrong. And moreover, you are a bad person. If your solution to, I now have the power to do anything, that's the infinity part of the infinity vomit. I can do anything with a snap of my fingers. If your answer is kill half the population, you just want to kill half the population. You are a fucking psychopath. Remember, Thanos was not the smart Titan. He was the mad Titan, as in the crazy one. He was literally insane. That's why his idea is insane. That's why his idea is bad. If you listen to his justification, it's like, oh, yeah, we should get rid of half of the humans. Fuck you. You are a bad person. Especially if you could do anything and you would just kill half the population. That's because given the opportunity, you would kill half the population, regardless of whether there was a resource crisis or not. If it really is a resource crisis, make more resources. If it really is just an inefficient use of resources, make people make use of the resources better. Or just create more infrastructure to distribute those resources efficiently. If you can do anything you want, snap your fingers and make some fucking infrastructure. Not kill half the population, you fucking psychopath. You're a bad person. I mean, it was obvious that Thanos was a bad person, but there's a bunch of people that don't get it because they're like, oh, Thanos was right. Ugh. And I don't know if they're joking. That's the scariest part. People be out there, Thanos was right, and I don't know if they're joking, because I know some of them are, but some of them aren't, and that should be frightening. Anyway. Conditional versus absolute convergence. The order that you add things up will change the sum in a conditional convergence series. This doesn't happen in absolute convergence. That's why absolute convergence is the stronger condition. Remember, what goes along with all of this is that the alternating series test only says convergence. You do not say diverges by the alternating series test, or converges conditionally by the alternating series test, or absolutely converges by the alternating series test. It just says converges. Then it's upon us to look at the rest of the series and say the series is absolutely convergent or conditionally convergent. Any questions? All right, so up next, I recall you're on part 6. Remember what this whole process is, this whole thing that we've been on about all week and most of last week is, it's not that the terms of the series go to 0, it's how the terms of the series are getting to 0. We've been spending this last week looking at all the different ways the terms of a series can drop down to 0. So let's talk about the ratio test, because once again, This is looking at how the terms of a series go to zero. Let's let AN be a series. What we're going to do in the ratio test is compare the series to itself. So unlike the comparison tests where we're comparing our given series to a known convergent or a known divergent series, we just take the series and compare the terms to themselves. Once again, this involves a limit as n goes to infinity. But we're going to be looking at the absolute value of an plus 1 over an. This is the limit from the ratio test. The limit as n goes to infinity of the absolute value of an plus 1 over an. If the limit from the ratio test is less than 1, then the series is absolutely convergent. If the limit from the ratio test is greater than 1, then the series is divergent. There's no such thing as absolute divergence. We could refer to conditional convergence as absolute divergence, but that would be really, really awkward. I'm sure there's some alternate universe out there where they refer to conditional convergence as absolutely divergent. And they probably think we're strange. We left out one case. If the limit from the ratio test is equal to 1, then the ratio test provides no conclusion. Well, or does not exist. Essentially, we can't compare it to 1. So this limit as n goes to infinity of the absolute value of an plus 1 over an. I'm going to refer to this as the limit from the ratio test. Clever title, I know. But there's a lot in all these tests for convergence, there's a lot of limit as n goes to infinity running around. So we can't just be saying the limit. So this is going to be the limit from the ratio test. We've also got a limit from the test for divergence. We've got a limit from the comparison test, or the limit comparison test. And we've got like some limits as n goes to infinity running around the alternating series test. There's a lot of limit as n goes to infinity. So if you tell me this is absolutely convergent because the limit is less than 1, I will say, what limit? And you're like, oh, there's my work showing the ratio test right there. I'm like, well, yeah, but what limit? Just saying the limit from the ratio test is less than 1. And then show me that the limit from the ratio test is less than 1. And if you say it's, then that's it. I'm just going to throw you out of class. So, well, it is less than 1, so it converges. Like, well, what are you referring to with it? It's clearly two different things. Get out. I'm just kidding. I wouldn't kick you out of the class. I'd have you expelled from the school. I'm just kidding. That's totally excessive. I'd flunk you and not sign off on you dropping the class. I'm just kidding. I don't have to sign off on you dropping the class. You could just decide to leave. So a couple of things to unpack here. We are comparing the terms of the series to the series itself. We're saying, what's the ratio of the next term to the term? An plus 1 over a. If that ratio is less than 1, then the terms are going to 0 fast enough. Remember what this is about. Are the terms going to 0 fast enough? This is another way of determining the terms are going to 0 fast enough. On this third point, the limit to the ratio test is equal to 1 or doesn't exist, then the ratio test provides no conclusion. Note that I didn't say there is no conclusion. I said the ratio test does not provide a conclusion. That means do something else. You have to do something other than the ratio test. So this part right here, the ratio test provides no conclusion. So do some other test. The ratio test is not going to do it. The ratio test is useless here. You have to do something else. Fasten these boards together with this screw. Oh, but I have a hammer, and a hammer does not work on screws. Therefore, I cannot fasten the boards together. No, that's not the conclusion. The hammer, the ratio test is the hammer in this case. That means go get a screwdriver and then fasten the boards together. The ratio test is just a tool, and this tool does not work in this case. Now, when does that case happen? The limit from the ratio test will be equal to 1 when you're dealing with a polynomial or a radical or a rational expression. So the ratio test is ineffective on expressions that are rational or radical. So the ratio of a polynomial at n plus 1 to a polynomial at n is going to be 1 every single time. So the only thing that's going to matter is the leading term. So we've got 5x and 7, or say 5 times the 7th power of x plus 1 divided by 5x to the 7th. The ratio is going to be 1. Five square roots of x plus 1 divided by 5 square roots of x. The ratio of, as n goes to infinity is going to be 1. The ratio test is blind to rational and radical factors. That's another way that I phrase it from time to time. The ratio test is blind to rational and radical factors. The ratio test does provide us comparison with factorial and exponential factors. So the ratio test is good for factorial and exponential factors. The ratio test is super effective and the tool of choice versus factorial or exponential factors. Factorials may be a new thing for us. N factorial is n times n minus 1 factorial. Okay, that was kind of a big move. N factorial is n times n minus 1 times n minus 2 factorial. Okay, I'm just kind of expanding on the dick move that I just used. This just keeps going to n times n minus 1 times n minus 2 times n minus 3. I'm not going to write factorial. I've already done that. Times 3 times 2 times 1. Just drop it all the way down to find the product of all the integers down to 1. Another way we could think of, say, 4 factorial. 4 factorial is 4 times 3 times 2 times 1. Just take 3 factorial and multiply by 4. Another way to think of n factorial is to say the number of ways to arrange n objects. N factorial is the number of arrangements of n objects. If you have one object, there is one arrangement. Put it on the table. If there are 2 objects, there are 2 arrangements. A, B, B, A. If there are 3 objects, there are 6 arrangements. Take the A, B, and B, A. Each one of those has 3 places to put C. A, B, C, A, C, B, C, A, B. B, A, C, B, C, A, C, B, A. Those are the 6 ways to arrange 3 objects. 4 factorial is 24. There are 24 ways to arrange 4 objects. Just take the 6 arrangements that we had from 3 factorial and notice that there are 4 places to put a 4th object. The reason that we want to know that n factorial is the number of arrangements of n objects is that 0 factorial is equal to 1. If you have no objects, there is 1 arrangement of those objects, the empty arrangement. Do not try to fit 0 factorial into one where you multiply all the stuff down to 1 because 0 is already on the wrong side of that definition. 0 factorial does not fit this definition. We stop at 1, 0 is already too far. But if we think of n factorial as the number of arrangements of n objects, then 0 factorial is 1. Don't try to justify 0 factorial equals 0 from this, because that will not work. If you're uncomfortable with that, then by definition, 0 factorial is 1. By authority. I told you that 0 factorial is 1, therefore 0 factorial is 1. That makes perfect sense. When we start doing more calculations with factorials, we'll see that the only reasonable choice for 0 factorial is 1. Partially because it's the number of arrangements of n objects, and there is 1 empty arrangement. All right, that's going to do it for today. 3 huge things today. 1 that we need to have more detail about. 3 big things today: conditional convergence, why it's weaker than absolute convergence. Number 2, the ratio test, which we'll look at in more detail tomorrow. And number 3, factorials, which we're going to look at in a lot of detail when we look at the ratio test. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.